Okay, this is right about where we left off. There's this game called Towers of Hanoi that I'm certain you're familiar with. It's this game, right? Maybe you don't know it in name, but this is the game. Have you ever seen anything that looks like this before? Yeah. And you may not have known, I mean, this is a kid's toy, right? But there's actually a set of rules allowed for this game. You have 3 pegs and a series of discs, plates, whatever you want to call them. And the goal is you have to get them all from this peg to another peg, all of them, such that they're in the same order, but you can only move one disc at a time. All the discs, like discs are never allowed to be placed on top of a disc that's smaller than it as well. So I can't like take this little disc off, put it there, and then put the bigger disc on top. That's against the rules. Can't do it. And finally, all discs must be on some peg at any given time with the exception of the one disc that's being moved. Okay? That's the rule. So imagine for a moment, do I have a GIF? I do. So like if you want to move the discs around, you would have to follow some like funky pattern like this. Right? Now take a moment and watch this pattern. Actually, hold on, let me make sure I am okay. Watch the pattern and see if you notice anything interesting. We'll just let it finish this cycle. When I said like we'll let it finish that cycle, you may have noticed we just moved the last one to where it's got to go. But interestingly enough, we were actually only about the halfway point. Anyways, that's the rule. There are several discs. Discs that can be added or moved from peg to peg. All discs vary in size. All discs start on one peg with the largest at the bottom and the smallest at the top. The goal is move them all from one to another such that you can only move one at a time. No bigger disc can be above a smaller disc, and all discs must be on some peg. So just to do a simple little example, let's say I've got 2 discs, and I want to move them to here. Can you see that reasonably well? Well, how do I do that? That's easy. You just take this one off, put it there. We'll call this like the temporary disk, okay? Now usually too often, depending on how you formulate the problem, which one's like the final destination doesn't really matter. All that really matters is that we move them off one of the disks to one of the other disks, but anyways. Then I move the bigger disk, and then I move the smaller disk. Problem solved, okay? But like if we have 3 disks, what happens? Okay, 1, 2, 3. Okay, let's make it there. All right, how do I do it? Well, okay, move the smaller disk here. Now I need to get this big one on another one, but I can't do that yet because I have to move this one, and I can't put it on top of that. So I guess it's got to go here. Well, and now I don't have any room, but I can move this guy there. And then I can move the big one. I can move the small one here. Move the middle one here, and then the small one I can go The point I'm making is I added one more disk. Suddenly I got a lot more shuffling around I got to do. But we can still do it. Just watch for a pattern here. Like, watch. I just showed you how to move it showed you how to move all the disks to that peg. Well, now we have to move all the disks, like, let's refresh. Okay, that's how we move 2 disks there. Now we need to move 3 disks, but moving 3 disks required moving the 2 disks as well. I don't know if you kind of see it, right? If I want to move 4 disks, I have to move 3 disks before I can move that 4th one. If I want to move 5 disks, I have to move 4. If I want to move 7 disks, I got to move 6. Yeah, there's a bit of a pattern there. I go back. Alt left arrow. Oh, neat. Neat. Okay. So Towers of Hanoi is it's a classic example where recursion comes up with a really nice, beautiful, succinct solution. Now I'm going to warn you. It's definitely not trivial. So don't beat yourself up if you struggle a little bit to wrap your head around it. But I'm going to do my best job to make this as accessible as possible. But don't worry if this one still feels like a big one. By the way, there is a legend that goes with this story. Where is it here? There's the legend. Here. Well, where's the legend? Ah, spoiler. All right, coming to the game, describing the game. I'll just explain it. So, no. So the legend goes, there's a sacred temple somewhere with sacred discs in it. Okay, I think there's like 52 discs or something. Let me double check. What did it say? 64. There's 64 discs. Okay? And they're very sacred, very important, and they're very fragile. Okay? And they are piled up on that side of the room. Okay? And there are 3 like holy spots in this temple space. Right? The place where they're sitting. A place over here where I got to move those discs to. And there's a place in the middle that is a temporary holding holy spot. Okay? They're the 3 pegs. Okay? If you're looking for the analogy here. So there are a series of, there's like a monk in there. Okay? Whose only purpose in life is to move these discs one at a time. And they have to move all 64 of them from there to there. But the rules are they can only move one at a time. They're very fragile, and you have to be very respectful towards these discs. So you can never place a bigger disc on top of a smaller one. And the discs must remain in their holy spots, the one of 3 holy super spots, as long as it's not the one I'm carrying. Okay? So me as the monk, I guess I'm allowed to be like, I'm okay to move them. But I got to, put them down. It's Towers of Hanoi with 64 discs, okay? And the legend says that once this monk finishes their job, which they are doing very diligently, the universe ends after they move 64 discs. All right? It is what it is. So anyways, so the Towers of Hanoi is a classic example. The trick is to consider, so we talk about this one recursively. The trick is to consider that whenever moving a disk, there is a source peg, a destination peg, and this like extra peg. A source holy spot, a destination holy spot, and a temporary allowed to put the plates down holy spot. Which one, when I'm talking about the game, which peg is designated the source, destination, and extra doesn't really matter. What I mean is, like right now, I want to move all of the disks to this peg. Right? But the end goal is to get them all over here, but like at any given time, like let's say this might sound silly, but go with me. I have 3 disks here. I want to move them all here. So here's my solution. By the way, this is the recursive solution. Move all, like if I have n disks here, okay? There's n of them. There's 3, but pretend there's a lot. Okay? If I want to move all of the disks from this source to this destination, what I can say is move all n minus 1 disks on top of the biggest one. I'm going to go back to 3 because I don't remember how many I drew. To here. Move the biggest one to here. Then move all of the remaining ones from the extra peg back to here. And now you're left going like, well, you skipped some steps. You can only move one at a time. You said move, like, let's go back to the 3 example. If I have 3, I say move these 2 on top to here. Okay? I need to get myself like a real one. It'll be easier to show you this with a real one. Move the biggest one here, and then take them from the extra peg and put them there. And you're like, well, hold on. You kind of skipped a step, because you're only allowed to move 1 disk at a time, and I just said move 2 of them. Well, really what I said was move all the ones on top. How do you move those? Oh, easy. Let's go back. So right now I have 2 disks that I need to move, that I'm saying move them to here. How do I do that? Well, think recursively. Think of this. Think that maybe I actually only have 2 disks that I have to move. How do I move those 2 disks? Oh, easy. Put the one on top to the extra peg, but that was the destination. It was the destination for the whole thing. We're going to deem it the extra peg for now. So I'm going to move the smallest disk here, then move the middle disk here, and then move from the smallest disk to here. That's how I move those 2. Do you see the recursive pattern? And oh, well now I solved that sub-problem. This is the same thing as like, how many people are behind you? You don't know, but ask the person behind you. You made a recursive call that just solved that problem. So we're going to just keep mixing and matching which one is the source and which one's the destination. I really need to get myself like a real one. I think someone in the department has one. I need to steal it from them. Any questions about like what I'm showing you? So further, what is considered the source, destination, extra peg is relative to when and what disks are being moved. So equipped with this information to move n disks from the source to the destination, simply move n minus 1 disks from the source peg to the extra peg, move the biggest disk, then move the n minus 1 disk from the extra peg to the final one. And like I said, you're like, but I just moved n minus 1 things at a time. Well, no, because we're going to move those n minus 1 things by doing the exact same process. So steps 1 and 3 might feel like cheating, but notice that they're the exact same recursive, like they're recursive calls. What one considers the source and extra peg will change when moving the n minus 1 disk. Looking at the first step, it says move n minus 1 disks from the source peg to the extra peg. Okay, so now what? Move the n minus 1 disks from the source peg to the extra peg, but changing which they are. Move the n minus 1th disk, then remove the extra ones again. and over and over and over and over and over again. But the extra and destination pegs are going to be different. So the extra peg when moving the n-1 disk, do you remember how like I showed you here how I want to move all of them from here to here, but in that sub-step I moved the extra one to here? Moved it there, and then it's going to do that the whole time. We repeat this pattern over and over and over again. Now, like I was saying, this is a non-trivial algorithm to grasp. But honestly, I think it's an easier algorithm. Like if I were to write this out, if I were to make you write this algorithm, like implement it, I think it would go easier for you if you didn't think about it too much. I think if you just followed the algorithm and you implemented it and hit run, it would work. And I suspect that if you start to mind muscle it too much, which at the end of the day, you probably want to do. You want to make sure you understand this stuff. But I think that would make things more difficult for you, as silly it is to say. I'm trying to think, do I have anything with me I could use? Nah, and the drawing doesn't work very well. But anyways. Any questions about Towers of Hanoi?
So like the universe implodes once?
Yeah, that's it. It's done, right? But how long would it take, right? Like, yeah, like how long would that take? Like if I have 64 disks and I can move one disk a second, let's say, this is a really fast monk, right? They can pick up a disk and run to the other side of the room within a second, but they're a fast monk. So let's say they can move one disk a second, right? There's only 64 disks, so how long will it take? Like 64 seconds? If so, we're in big trouble. How long would it take?
Like 2 to the 64.
Yeah, I think it's going to be like 2 to the 64, right? Because let's count. If I have one disk to move, I have one disk to move. Right? That's how many steps I have to do. I just go from source to destination. Done. One. So let's say, okay, 1 is 1. If I have 2 disks, I've got like, well, I've got to move 1, 2, 3. Right? Do you see how like it's actually 3 steps I have to move? I move the one disk twice. So 2 is 3. Let's say 3. So if I have 3 disks, I have to move 1 there, 1 there, that's 2, 3, 4, 5, 6, 7. Okay, yeah. 4, who wants to guess it's probably 15 or something? Let's count it. I'm probably going to lose count because this is a lot now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I feel like I maybe messed up. I think I messed up.
Like 2 moves ago. You put a smaller.
Did I? Yeah? That one should have been somewhere else?
Yeah. So the first one's supposed to have this. Like
So totally that was probably 15.
Okay. Yeah.
What do you think if I did 5? How many do you think we'd have?
24.
You think 31? I think it's probably 31. Something. I don't know why. I just got this feeling. What about 6? What would it be? 63? Yeah?
Possibly the next one would be 127.
120. Do you think, yeah, maybe 127? So 8. So if you haven't noticed, the pattern is like 2 to the power of n minus 1. Yeah? Yeah? So what is 2 to the power 64 minus 1? Times 10 to the 19. Did you minus the 1 though?
No, because I didn't get that precise.
No, that was the joke. Times 10 to the 19. But did you subtract 1?
That's a lot of seconds, but like that's.
Well, how many, okay, if that's seconds, they can move 1 a second. So that's how many seconds. How many minutes? Divide that by 60.
3.07 times 10 to the 17.
Okay, that's how many minutes. Divide it by 60 to tell us how many hours we got.
5.12 times 10 to the 15.
Okay, so that's how many hours.
24 to get days.
How many days we got?
2.13 times 10 to the 14. Let's do years.
Yeah, how many years is that?
Okay, we got a few.
And, just to be precise, we're going to do 365.25.
Okay, good. You don't want to miss those.
We got...
Isn't it like 2504 or something silly?
Currently, we are at 584 billion.
584 billion.
To be fair, that'll cut the universe short by a significant margin.
Yeah, well. At the end of the day, yeah. Maybe that, but you know what? Maybe the monk gets older, gets slower in their old age, so maybe we'll be fine. I don't know, right?
Or maybe just the.
That monk is zooming.
Yeah.
He 1 a second, he's running around like crazy.
He's gonna slow down eventually.
He's got it. Maybe he's got brakes. We don't know.
The human limit.
Although maybe it counts as like exercise, so he gets faster.
Oh, I don't know.
Adrenaline pushing him through like the 5.
Point being,
You stop to take breaks.
like this little example, this little legend goes to show you, legend, obviously it's probably not true. Exponential growth, just 64 plates. It's a lot of seconds. That's a lot of steps. Exponential growth, kind of, it is what it is. Okay, any questions about that? Yeah.
Hours of the noise. You said the repetitiveness of the movements, but there would be some change after those three first movements.
The changes are what the source and what the destination pegs are. That's really it. Everything else is the same process. Move everything on top to some middle ground. Move the biggest one to where you want it to go, but the biggest one might not actually be the biggest one in the whole picture, but the biggest one in the number that you want to move, right? So that's kind of the trick to it there. Okay, any other questions before we move on to the next thing? Okay, for the purpose of this topic, searching is going to be defined as the process of looking for a specific thing in a collection of some things to know whether or not it exists in that collection. Now, the reason I'm emphasizing this is we know that we've done like linear searches before, and linear search is a far more general idea, like am I looking for the biggest number, the smallest number, does it exist, where does it exist, does it exist within a range, all these different things. Here we're just saying like, is it there or not? So does a given number exist within an array of numbers would be like the problem I'm talking about here. So to write an algorithm to solve this problem, all that we have to do, I'm not talking about whether or not the algorithm is good or not. All I have to do is write an algorithm to solve this problem. All we need to do is say if it is in fact there or not. Okay? That's it. It doesn't need to be a good one. It just needs to be like, will it do its job? That's all that's required. Any algorithm that works will be deemed sufficient. However, the focus here will be on two intuitive ideas that people commonly use, one way or another, throughout their lives. A linear search and an interpolation search, both of which I know you're used to. We've already kind of talked about interpolation search before with a slightly different name, but interpolation search is just a fancy, it's like a binary search really is what we're talking about. We've talked about this before. Throughout this topic, the thing being searched for will be referred to as needle, and the thing being searched will be called haystack, okay? That's the terminology we're going to use so we don't get lost. All right? So a linear search. Start at the beginning. So how does it work? Start at the beginning of the haystack and sequentially look at each thing one at a time until we find the thing we're looking for, until we find needle. If needle is found at any point along the way, we found it. It is in fact there. If I start searching a list and the thing I'm looking for is at the beginning, it's there. If it's at the end, it's there. If it's anywhere in between, it's there. As soon as I find it, I can conclude that it is in fact there. It's not until I look at everything, and all of those things I looked at were never the thing I was looking for, that's when I can only conclude that that thing is in fact not there. So notice that this description of the algorithm does not go into any details though. I mean, I give you the details, that's the algorithm. But if I say go implement this, like, I didn't give you code, I didn't give you pseudocode, I just told you like that's the idea. Start at the beginning, look at each thing. If you find it, you're done. If you don't, keep going until you run out of room, and if you run out of things to look at, it's not there. So it's a high-level description of an algorithm. If I asked you to go implement this algorithm, you've got a couple of choices to make. Even without looking at this algorithm, assuming a realistic implementation, this algorithm should be linear. Because, like, at best it should be linear. Maybe you come up with some with ridiculous implementation that's just deliberately terrible, which you could do if you wanted. But like at best it's linear because the worst case scenario is you got to look at all the things. You will only ever conclude that something is not there the moment you get to the end and you never found it. So you have to have had looked at everything before you can conclude that the thing is not there. So it's going to be linear. Worst case scenario, every element in the haystack was looked at before making any conclusion. Best case scenario is the needle is the first element, so, okay, it's one thing, but we often don't really care about the best case scenario. We always think like, well, how bad is it going to be? And on average, the thing will be like in the middle, right? Either it's there at the beginning or at the end, or the second one or the second line. On average, it'll be in the middle, but like we've talked before, if it's about halfway through n, if I have to look at, on average, half the things, that's a coefficient, and it's not about the absolute number of things. It's if I double it, it still grows like n. If I say 1/2 n versus 2 times 1/2 of n, how much did this change between these things? Here, I should put the 2 there actually. How much did it change? Well, it's like linearly, okay? Just to emphasize the fact like why we don't care about the coefficients. It's still linear. So example, linear collection of data with a linear search. To guarantee if some needle exists within this haystack, each element must be looked at. We must. So there's 15 things there, okay? Is this the thing I'm looking for? 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 Now, in this example here, I've got all of the numbers from 1 to 15 in order, right? So there's no gaps, okay? But remember, when you're looking, if this is an algorithm looking at this collection of data, it doesn't know what's coming next, right? Like we look at it and go like, oh yeah, but we had to like look at it all to make that conclusion. So don't think that the orderness of this really matters. For a linear search, the numbers could be like 7, 99, 4, 4 again, 4 again, 44, right? Like the order and whatever, we don't know what it is. Okay? All right. Below is a generic implementation of a linear search on an array of type T. So there we go. Have a look at this code. If this code puzzles you at this stage, come see me because we've got a problem. What do we have? Okay, public static, it's generic. It's a generic static method. We have this thing there. Int, I guess this one here I'm going to return the index of where it is, okay? Okay? Int, iterative linear search, it takes the needle, it takes a haystack, a needle of type T. the haystack is an array of type T. From 0 to the length of the haystack, I++, objects.equals is the current thing equal to the thing I'm looking for. If it is, return I, and if we ever get to the end, we return not found. Presumably not found is some constant that is that sentinel value, which typically we've used like -1. So there we go. And by the way, when I say like if any of this confuses you, I'm not so much talking about the specifics of the Java code, I'm talking about the iterative algorithm, right? So yeah, if this algorithm you should be very familiar with by this stage. We've been using this general idea since assignment 1 in 161. The iterative implementation is very similar to the high-level description. Start at index 0, the beginning of the haystack. If the element at index I is the needle, conclude that it's there. Otherwise, continue increment I. If the end of the haystack is reached and we never found needle, then it must not be there. That's the algorithm, right? So there's clearly a nice, clear relationship between this description. If the needle is found, conclude that it's there. Okay, we start at the beginning. If the needle's found, it's there. If it's not, keep looking. If we get to the end and we never find it, it's not there. That's what this is. Start at the beginning. If we find it, good. If we don't, keep looking. And if we get to the end, it's not there. That's the algorithm. We see? Cool. Now, here's a recursive implementation. Look at this code. Make it make sense. Nothing about this should be overwhelming to you right now. Pay attention to the parameters that you have. Yeah.
So with this one, you could start at any point.
Yeah. Yeah. Typically, do I say that? I don't. Typically, sometimes you would have like a helper method. We'll see examples of this when we get to the trees. Typically, you have a helper method where when you call it the first time, you don't specify the current index. So you actually have like two versions of the method. You'll see examples of that later. Don't get too bogged down by that. Yeah.
So kind of like you have one that has the default one at like 0.
Yeah, for this like helper method, where the helper method doesn't take an index, but all it does is call this one with 0. Often you would have like a public and private facing ones. But don't worry about that too much right now. Let's focus on what this is saying. Needle, haystack, current index. If current index is the length, well, that means somehow current index is that we got to the end. Okay, it's not there. Return not found. Otherwise, if objects equals, if we find what we're looking for, return the index. Otherwise, call recursive search on needle haystack, but the next index. That's it. Now, you look at this code and you're like, well, that code is clearly quite different than this code. Would you agree? Yeah. It's the same algorithm, though. The algorithm is exactly the same. I call it like this. We start at the beginning. If we find what we're looking for, we're done. If not, continue looking at the next index, and if we ever get to the end and we never find it, we never found it. The algorithm is exactly the same. The code and like style of the code was very different. One was iterative, one was recursive. But the actual underlying algorithm that we're doing is exactly the same. So yeah, it may seem quite different, but it's not. Start at the beginning. The order might feel like a little different, but that's not really important here. If the end of the haystack is reached without finding the needle, then conclude that it's not there. If the element at index current index is the needle, conclude that it is in fact there. Otherwise, continue by calling it again with the next index. Yeah.
Couldn't you then like skip over the needle in this case by making the current index start at like 2 or something?
You could. Yeah. Yeah.
Okay. I don't know. The other one just seems like you're always going to find the needle regardless, but that one you could theoretically just skip over it.
Well, that's why, like we were saying, you would often, in cases like this, you would often make a separate function that you call, and we'll see examples of this, but you make another function that you call that only takes 2 arguments, the needle and the haystack. And maybe you make this one private or something. So you call the public one that only takes 2, and all it ever does is call this one with a 0. So, but it's public facing, so no one could ever actually call it starting at anything other than 0. You call it, and then it goes straight to calling the one where it starts it at the correct index. Now we're just talking about misusing code, and I mean you can misuse code you can use functions wrong all you want. Yeah. Yeah.
This has similar computation complexity.
You tell me. Let's ask everybody. What's the computational complexity comparison between the iterative one and this one? The question is always, how many times will this code get run relative to n? And how will it grow relative to n? N. It's still linear, right? If the length is 10, every time this gets called, assuming I start at 0, it'll get called for when it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and I guess 10. Right? Every time it's called, it can at most make one more call. So there'll always be like a nice linear chain of calls. It's still going to be linear. The Fibonacci was different because each one made 2, and each of those made 2, so 4. Each of those made 2, so 8, and so on and so on and so on, and that's where we get our crazy problems. Any questions about that? Now, binary search. So if I'm looking for page 554 in a roughly 1,000 page textbook, it would be reasonable, like if anyone in here have a textbook with them? You do? Grab it. Oh, perfect. Classics of Western Philosophy, 8th edition. All right. I want to find how many pages are in here? Over 1,000. Okay. I want to find page 700. How do I do that? Do I do this? No. No, not there yet. No, I'm not even at the numbered pages. My goodness. Okay, Plato, page 1. Is that 700? And let's say I'm looking for 700. Okay, is that it? No. Is that it? No. Is that it? No. No, still not there. How long is this going to take me? And yeah. I got to turn the page quite a few times, right? Is this how you would look for that? No. You would do something normal. You would go like, here? Whoa. I'm looking at page 728. Okay, actually, let's do a little, I'm going to change it. Pretend I didn't do that. I'm looking at page 630. Not bad. Okay? Now, I'm looking for page 700. Over here are pages less than 630. Over here are pages more than 630. And I'm looking for page 700. I have about 630 pages over here. And let's say, I don't know, maybe about 600-ish over here. It's a pretty big book, right? This is about somewhere in the middle, right? If I want to continue searching, where should I look? Should I look over here? No, that's ridiculous. Because I'm looking for 700, and these ones are all less than 630. Can the page 700 possibly exist over here? Not unless they numbered this book very poorly. I can't do it. So, I'm able to look at this page here, okay? These two pages, really. And I'm able to eliminate about half of the things. I don't need to look over here anymore, right? So let's go again. I overshot it. I'm looking at it, page 830. Okay? Now, I'm looking for page 700. All of the pages over here are bigger than 830. All the pages in here are somewhere between 630 and 830. And I want to find 700. It must be in here. Ooh, 716. Okay. 688, oh my. 700, got it, there we go, right? So how did I do it? Well, I kept, first of all, I eyeballed the book and thought like, well, it must be around here, right? Because I know a little bit about the information in here. What do I know about the pages in here? One, I know they are ordered. And two, I know that they are like all of the numbers in order, right? So like if I'm looking for the page 700 and I know there's so many in there, I have an idea about where it's going to be. Now that might not always be the case. We might have data that's ordered, but let's say my data is like 1, 2, 3, 99, there. And I'm like, oh, I'm looking for, no, that's not a good example. Why can't I think of a good example here? 3, 3, 3, 1799, right? And I say, find the number 50, right? And you're like, well, okay, it's probably around the middle, right? Well, that's not going to help me very much. Because again, like, that book, the pages are all there and in order, right? Now, in this particular example, they're not, right? So we don't always have the case. The data might be ordered, but how evenly distributed those pages are might not be great. So this interpolation search won't work always that well, but the general idea of a binary search will. Obviously, I found the page 700 a lot faster that way than I would have if I kept going like this, one at a time. Why though? Obviously we know that it would work, but why? And the reason why is because every time in the linear search, every time I look at something and it's not what I'm looking for, how many things did I eliminate from my search? 1. I could turn the page. Okay? But when I did something like this, and now I'm getting too lucky, I'm looking at page 770, and I'm looking for 700. And I know to look over here. How many things did I eliminate from my search? All of these. With everything I look at, I'm able to eliminate a lot of information. We want to make decisions. We want to look at things such that we will eliminate the most number of things possible. Okay? Okay? Okay. So that's why it's better, is because every time I make a decision, I'm able to gain a lot more information effectively. I'm able to eliminate more. My confidence and my ability to know that it's in like the smaller set is way more. It's way more powerful here. But that all depends on one very important thing. The data must be ordered. Otherwise, when I'm looking at page 770, if there's no guarantee that the number 700 is on this side, I can't make that conclusion, right? All right, activity time, real quick. Pass this back down. Give me, so I'm giving you this, but show me, write code to 1, create an array with stuff in it. It could be fairly short. 2, find whether or not a specific element is in, I guess the index of a specific element is in there. And 3, you must do it recursively. That function right there.